Good day, everyone. Today, we are going to present our study entitled Complementary Circuit Breaker with additional feature using RFID with overcurrent detection and tripping monitoring. The word complementary in our title means making the circuit breaker better, but by combining it to our usual circuit breaker that we used in our home, and then adding access control, which was the RFID, tripping monitoring that can be automatically or manually, and then the system's current detection. Background of the study: information is gathered, analyzed, and transmitted on the internet through mobile phone, computers, and other digital electronics. Therefore, the role of electric power industry is to ensure that energy consumers are able to receive dependable and undisturbed power supply. Circuit breaker as protective equipment used to minimize or eliminate the effects brought upon by faults in an electrical system. So it is expected that when a fault is detected, the circuit breaker will trip and then isolate the affected line. Unresolved fault may lead to or damage to plants due to thermal effects of fault current, loss of system stability, loss of supply to loads, and then danger to human life. So apart from that, the time consumed in repairing the damaged line prolongs the system downtime, which may affect your business and their consumers. Password implementation to protect linemen, operators working in electrical grids. So there is a lack of communication between the substation and linemen, operators that can lead to accidental switching that need to be prevented. So for the statement of the problem, electrical downtime cannot be totally eliminated, but it can be prevented by monitoring and regular maintenance. So this study aims to provide a security scheme to prevent this problem, including how to add a security feature in a circuit breaker without compromising its basic function, and then how to notify the authorized personnel about the status changes in a circuit breaker. So for the objectives of this study, the main objective of this research is to implement a security scheme on an actual circuit breaker, specifically to model a circuit breaker with added security feature using microcontroller and relays, to apply RFID system as input peripheral of the circuit breaker, and then lastly to use a GSM technology for the circuit breaker. So for the rationale of the study, electric accidents, according to the international statistics, are the deadliest types of accident. Then power outage is considerably one of the major hazards that poses a threat in the operation of the business industries. Then having a server, critical network connections, or mass storage device going down due to power outage may obstruct the business normal operations. So because of equipment failure, optimization and consistency models of electric equipment, they are used to maintain their working conditions, quantitatively refine maintenance plans for the maximum reliability and minimum expense. For the scope and the limitations, RFID is subdivided to low risk, medium risk, and high risk load. So for the low risk, it is for the technician. Medium risk and low risk can be controlled by the supervisor, while for the manager, he can control low risk, medium risk, and at the same time high risk. The rated amperes is up to 15 amperes only. So the system was set up to 12 amperes or greater than that. It will be considered an overcurrent once it was met. And then lastly is for the RFID security. Also, there are circumstances that the RFID cards was being cloned, so it's not the scope for a study. And for the conceptual framework, so the inputs consist of the existing circuit breakers that readily available in the market. Then the selected circuit breaker is a two-coil miniature circuit breaker rated at 15 amperes. So the microcontroller, the RFID system, and relays will be integrated to produce the circuit breaker with access control, which was the output. The review of related literature, according to Abbas Gurbani, Mashadi, and Damchi, corrective and protection approach will effectively mitigate the risk of failure and delay investment in replacing old circuit breakers due to its effects on the reliability and life cycle. While for the overcurrent protection by T. Kell and J. Jagger, overcurrent protection is a cost-effective. It is also useful in delivery networks with disturbed generation. So networks that require quicker and limited fault clearing without the use of expensive networking facilities in comparison to other security schemes. So the basic function of a switchgear is to create and rule electrical circuits that must be dependable in static situations while still being successful instantly when called upon to execute some switching action. And by lastly, power outage by Ascari that who perform a study and the result indicates that the businesses normally invest in standby electrical generator, insurance, and uninterruptible power supply. So sudden loss of power supply on the end may result to some adverse or unfavorable effect. Related studies claim that password implementation on a circuit breaker can save the lives of linemen working in a faulty line. So for our first picture by Ishwar, who proposed a system that uses a PIC microcontroller as its controlling device and MOSFET driven electromechanical relays as its switching device. For the second picture by Abdallah, design a system that trips at a rated current of 500 milliamps that uses a 4x4 number keypad as its input peripheral. Lastly, for the third picture by Padhen, that use a similar approach but include a dual tone multi-frequency or the DTMF module in the system.
Methodology. To explain the methods used in the study, we'll start with the block diagram, just to give an overview of how the system would work. Okay, so this is how a typical electrical system would look like. There would be a supply that is connected to a load, and in between that, there would be a circuit breaker. If the circuit breaker is turned on, then the current would flow to the load. But if it is turned off, then it would appear as an open circuit and no current should flow to the load. This is one of the problems that was stated earlier because virtually anyone who has access to the electrical rooms or to the location of the circuit breakers would have the ability to cut off the power supply. This is an issue because some loads are considered to be critical, such as the ones that is presented in the table in this slide. These are critical loads and they should receive a power supply 24/7. They should receive continuous power supply or 24/7. So to address this problem, we have added access control into the circuit breaker by using microcontroller, RFID, and relays. To make things simpler, or to explain this concept in a simple manner, we will just be using one branch because in the prototype, this concept of access control actually works the same or similar with the other branches. As you can see in the figure, there is a normally closed relay connected in series with the load. When activated, the contacts of this relay should switch, thus causing this circuit to happen, thus causing an open circuit. So by this concept, we can say that we can turn off the power supply in a branch for an indefinite time as long as the normally closed relay is activated. This is how the concept of access control works. We have connected an RFID system, and then the microcontroller is programmed to identify which card is tapped by the user. Then that card would have a corresponding branch uh, that it can turn off or it can lock off. There are three card designations. Card 1 can be used for branch 1, card 2 can be used for either branch 2 or 3, then card 3 can be used for all branches. Okay, so this is the actual prototype. These are the circuit breakers. These are the loads. This is load 1, this is load 2, and then this is load 3. And then on this part is the microcontroller, RFID, and relays. Uh, this is what we created, the system that we created to complement these circuit breakers. To demonstrate the access control, we have prepared. So in this video, I was using card number 3 to lock off branch number 1. This one, I was using the same card to lock off branch number 2. And lastly, uh, this is card 3 used to lock or unlock branch number 3. And if you notice, even if the circuit breaker is turned on, no current is flowing through the load. Again, this is because of the normally closed relay getting activated. To monitor overcurrent, we have placed a current sensor in series with the load. This sensor is capable of measuring the load current. And in this prototype, since we are using a 15 ampere circuit, the maximum load current is set to be 12 amperes. In this video, we'll be presenting or we'll be demonstrating how this overcurrent is being monitored. So as you can see, here branch 2 is overloaded, so the load current is 14 amperes, and then it automatically tripped, and then after that the GSM module have sent a text message to the registered number. To perform trip monitoring, by the way, trip monitoring refers to the system identifying what type of trip has occurred in the circuit breaker. It can either be manual trip or automatic trip. In this video, we'll be demonstrating how manual trip is detected and what the system response should be. So, as you can see, right after I turned off the circuit breaker, power is immediately restored in the affected branch, and then a text message is sent to the user. As you may have seen in the previous video, we have turned off the circuit breaker, but after a few seconds, the power supply is restored to the load. What happened there is that we have connected a 230 volts AC to 5 volts DC converter, which is this one, with the inputs of the converter. So for example, we'll be using converter number 1. With the inputs of the converter, tap into the output of the circuit breaker, of the corresponding circuit breaker. Since we turned off the circuit breaker, then there should be a 0 volts signal here, resulting to 0 volts signal on this terminal, and again resulting into a 0 volt signal on the output terminals of the converter. Since the terminals of this converter, the output terminals of this converter is connected to the microcontroller, then we can generate a signal here which is 0 volts or 5 volts. And again, this is 0 volts if this is 0 volts if the circuit breaker is turned off, but if it is turned on, then there will be 230 volt signal here, 230 volt signal here, and then 5 volts signal here, resulting to a 5 volts signal as read by the microcontroller. So this microcontroller is programmed to identify a reading of 5 volts as a normal state. And then if it reads 0 volts, then it means that the circuit breaker is assumed to be manually tripped. Now for the power restoration, it is the normally open relay which is responsible, since it is placed parallel to the circuit breaker, thus providing a bypass route for current to flow to the load. Again, this normally open relay is also controlled by the microcontroller. And for the automatic trip, this refers to when overcurrent is detected in the system. So this is similar to the video that was presented earlier. These are the actual messages, text messages sent by the system when manual trip or automatic trip has occurred. A web page is also created to store the data gathered. This is where the system uploads the load current of each branch. It is taken every 15 minutes. It also contains the type of trip that occurred in the circuit breaker and which among the circuit breakers have tripped. To assess the system performance, we have tested the following equipment used in the prototype. Number 1 is the current sensor. Number 2 is the GSM module, and number 3 is the RFID system. For the current sensor, we have calculated the discrepancies using this formula. CL refers to the clamp meter reading, and then S refers to the system reading. There are two possible categories for the discrepancy. It can either be greater than or equal to 10%, or it can be less than 10%. In this study, we have predicted that all current readings gathered would be less than 10%. Since 15 readings are gathered per branch per day, and the data gathering lasted for a week. The sample size is predetermined to be 315. This number is the sample size to be used for the error matrix. Based from the error matrix, the accuracy and sensitivity of the current sensor can be computed as follows. For the GSM module, we followed Bayes' theorem by filling up this table as shown here in the slide. The following probabilities can be calculated. Each circuit breaker are deliberately turned off 5 times a day to simulate manual trip. After that, each branch are overloaded 5 times a day to simulate overcurrent. In total, there are 105 manual trips and 105 automatic trips that happened resulting to a sample size of 210. So again, these are the probabilities that can be calculated. And then finally, we can calculate the probability that a text message is sent after a manual trip or automatic trip have occurred in the circuit breaker. For the RFID system, the percent reliability is calculated using this table and formula. Pass means the top card is successfully identified by the microcontroller, and then fail means the top card is not recognized by the microcontroller. Each card is tapped 15 times a day per branch. For card 1, it is tested for 105 times only. For card 2, it is 210 times only. And for card 3, it is 315 times. Results. So after calculating the discrepancies of the 315 paired current readings, the highest discrepancy turned out to be 5.72% only, while the lowest was 0%. Based on this, we have filled up this error matrix. So with these values, we then calculated the accuracy and then the sensitivity, which turned out to be 100% for both. And these are the results. There are 105 text messages sent out of 105 manual trips that occurred. There are also 105 text messages sent out of 105 automatic trips that occurred. And then the text not sent is 0 for both. From these calculations, it turned out that the probability or chances that a text message is sent when manual trip or automatic trip have occurred is 100%. Lastly, for the RFID system, it turned out that all 3 cards have passed in each attempt. The microcontroller were able to recognize each card and were able to lock or unlock the branch specified with respect to the top card.
For our conclusion, setting the RFID system as an access control device is proven to be effective with 100% reliability rating. So each of the cards used were read during each attempt and the system performed the corresponding task with respect to the top card. While for the system current versus clamp meter, it resulted that there is no significant difference between the two. The results also showed percentage error ranging from 0% to 5.7%, only which means that the discrepancies fall below the limit, which is 10%. While for the GSM, the notification system also delivered 100% reliability after a number of trials and tests performed. So through the notifications, the user is alerted when a manual trip or automatic trip has occurred in the circuit breaker. Our recommendations: higher loads. The study set the ampere with the maximum load to 12 amperes. So an improvement of this study would be applying higher loads. This will provide the current readings that were used in actual commercial and industrial establishments. For short circuit, in this study, short circuit fault was not considered, although it falls under overcurrent conditions. So future researchers may include this in assessing the system performance. They may also want to investigate on the amount of power losses caused by the system. And lastly, for the semiconductor devices, instead of numbers of relays used, the future researchers can do power electronics, where they will create a circuit consisting of power MOSFETs, transistors, and etc. that will be assembled into one MCU. And that's our capstone project. Thank you for listening.